Okay, so I'm going to try to finish this problem off with part D, solve the differential equation. We've already looked at what happens initially at t equals 0 and t goes to infinity, um, just to sketch these in on this convenient little plot of q versus t. And making a plot is something they're also going to want you to do sometimes. What they usually want you to do is just sketch a plot. So when they say sketch, what you want to do is sort of get the basic features right and maybe show one or two important values, but you don't need to go and calculate points and plot something nicely. So for example, here at time t equals 0, which is right here, we're going to have q equals 0, and we're going to have dq dt as some positive value EMF divided by r. So I'm going to show something like that, okay, to start with. As t goes to infinity, q is going to approach this constant value of c times EMF, and dq dt is going to go to 0, which is what you'd expect if q is approaching a constant value. So I'm just going to draw sort of a horizontal asymptote there and label that with the steady state value, capacitance times EMF. Okay, so pretend that looks good. Yeah, whatever. Okay, so we're going to approach that over a long time, and then what's going to happen is as time passes, we're going to sort of decay to that. Okay, you might guess from looking at the equation here that you're going to have some kind of exponential decay. Makes sense, right? You're going to have, like, if you have an e to the t in q, then when you differentiate that here, you're going to also have an e to the t term, or an e to the, some constant times t. And so you could sort of go with that and try to construct sort of the most general exponential decay function. And so I'm going to call this method 1, which I'm not going to do, but method 1 would be to let q of t have a form of some constant a times e to the negative some constant b times t, okay, plus then some other constant c. So this gives it an, actually, no, you don't want to do c because that's the capacitance. So plus d, where a, b, and d are all constants. This d here gives you something that goes in q of t that is going to come out equal to this, but when you differentiate and do dq dt, the d goes away. The a is going to stay attached to that, and then the b is going to pop down when you take the derivative and find dq dt. So you can take dq dt for this, plug it in with these conditions, and then you just solve for a, b, and d. Okay, I'm going to try method 2, which is more straightforward. I mean, I sort of did some variation of method 1 in class, okay? But for method 2, what I'm going to do is I'm going to actually take this and separate the variables and integrate. So what we want to do with this equation is get all of our q's on one side and all of our t's on the other. And so not counting this of t here. So how do I want to do this? Let's see. What I want to do is go dq dt equals EMF over R, okay, minus 1 over RC times Q, okay, times Q, fine. And then I'm going to take that there, and now this is where it gets tricky. I'm going to say dq equals, and then I'm going to go 1 over r. So I'm going to factor out the 1 over the r on the left side. I'm going to multiply the dt over. And EMF minus 1 over c times q, and then the dt. So that's where I get to there. And then I want to get the q over here with the dq. And to do that, I just divide this whole term, everything but the dt, over like that. So then I'm going to get, let me actually make this like that. I'm going to have an r times dt over, and then I'm going to get the EMF minus 1 over c times q. Okay, and there's our quantity there. The r comes up to, oh, it's not the dt, it's a dq. So sorry about that. And no, wrong size eraser. Squeak it, squeak it, squeak it, squeak it. And then this here, I think is my pen. There we go. So this is going to be dq over this, and then that is going to equal dt. And so then all I'm doing is I'm just going to integrate now, and I'm going to just be, well, I'll tell you what, I'm going to make my integral out here. So R, and I'm going to integrate dq over EMF minus 1 over c times q, and this is going to be, I'm going to go from, we're integrating dq, so I'm going to go from q equals 0 initially to q equals, I guess what I'm going to have to do is q equals q as a function of time, okay, to do this properly. And so I'm going to make this q squiggle, dq squiggle, q squiggle, and then that's going to equal integral from t equals 0, and actually this should be q squiggle, from t squiggle equals 0 to t squiggle equals t, and go d, let me move it down a little, dt squiggle. Okay, so now this guy here, we basically have the denominator here, and we want the numerator to be the derivative of the denominator. Okay, so I'm going to have to go negative 1 over c. I'm just sort of scratching this. Whoa, crap. Let's see. Window. Zoom. No. Oh, God. Let's see. And that's not something I can undo. Oh, my God. Oh, and now, of course. Okay, so I'm going to get up to 100%, and I'm going to move. Sorry. Yes, welcome to I should have just paused. All right. Sorry about that. So negative 1 over c. So I'm plugging in the negative 1 over c there, which means I have to plug in a negative c out front. Okay. And so yunk. Okay. So then this is going to become, this is just going to be, the left side is going to be negative cr, and then the integral, when you evaluate it, is going to be natural log of EMF minus 1 over c times q squiggle evaluated here, which is going to be q of t, okay, over EMF minus, and that's going to be 1 over c, and q initially down here is 0, so this is just going to be minus 0, so I'm going to actually just leave that as that, okay. So that's going to be the left-hand side, and that is going to equal, sorry for scrunching this in, that's just going to be t minus 0, okay. So now what I'm going to do is take this, and the next line is going to be natural log of, and I'm going to divide this out here, so this is going to be natural log of 1 minus, is this right? I hope this is right. 1 minus 1 over capacitance EMF times Q, okay, is going to equal, and I'm taking the CR and multiplying over there to be negative T over RC. Take the exponential both sides, you get 1 minus Q over CE, whoops, not E, EMF E, curly E, okay, equals e to the negative T over RC. And then at last, what this is going to come out to is, and I'm going to just grab some space up here, and, well, I'm going to just wipe out all this crap up to here. Okay, and right in here, that the answer is, right, Q is equal to C times EMF times 1 minus e to the negative time over RC. Okay, so this here now is your answer. You can see, in fact, that this will approach capacitance times EMF in the steady state. You can see also that time t equals 0, it will be equal to 0, and all the good stuff. You can differentiate dq dt if you want to find the current over time, and yeah, that's about it. An exercise, you can verify that RC, verify that the units of RC are in fact time. And the other exercise you can do is, so it's exercise 1. Exercise 2 is do it with no power supply, or no, you can sort of say do it without, yeah, okay, so do it without the power supply, do it without the EMF. And you have to start now with Q equals some initial Q at time 0, and then analyze the discharge. And you'll get a very similar answer. Anyway, there you go. Hope that helps.